The computer era is the final stage in the history of pi. And recall from the last video that in 1946, Daniel Ferguson was able to find 620 digits of pi. And 3 years later, in 1949, the mathematicians John Wrench Jr. and Levi Smith found 1,120 digits of pi using a desk calculator. And in this same year, a team led by John von Neumann and George Reitweisner used the ENIAC computer, which is the first electronic general-purpose computer. And to give you an idea of how big this is, it weighed about 60,000 pounds. And using this computer, they were able to find 2,037 digits, and it took them 70 hours. And to give you an idea of how great of an accomplishment this was, we need to look back to the year 1873 with the mathematician William Shanks, who found 707 digits of pi, and this took him 15 years of his life to calculate this. And it should be noted that there was an error at the 528th digit. So every digit after this was wrong. And the error was actually noticed by Daniel Ferguson in 1946 when he calculated his 620 digits. So with the ENIAC computer, you can see that the computer was able to calculate almost 3 times as many digits, but it only took 70 hours compared to 15 years for only a third of the digits. And after the invention of this computer, the calculations for pi really took off. And in 1957, the record reached 7,480 digits, and in 1958, the record surpassed 10,000 digits, and in 1961, the record surpassed 100,000 digits. And in the year 1973, the record surpassed 1 million digits of pi. And all of these results were found using Machin-like formulas. And in the year 1985, the record reached 17 million digits of pi. And this result was found by Bill Gosper. And to understand how he found this many digits, we have to go back to the year 1910. And in this year, the mostly self-taught Indian mathematician Ramanujan discovered many quickly converging infinite sums to find pi. And as an example, we have 1 divided by pi is equal to twice the square root of 2 divided by 9,801 multiplied by the infinite sum, and here I'll use the shorthand notation for sum, which I'll explain in a moment if you're unfamiliar with it. And each term of this infinite sum has the pattern of 4 times k factorial. And if you don't remember factorial, for instance, 4 factorial is just 4 times 3 times 2 times 1. And this 4k factorial is multiplied by 1,103 plus 26,390 multiplied by k. And this is all divided by k factorial to the 4th power multiplied by 396 to the 4 times k. And to give you a more intuitive understanding of this summation notation, I'll show you an example with a much simpler infinite sum. So if we have the sum from k equals 1 to infinity of 1 divided by k squared, then the way to look at this is to start with k equals 1 and plug that into the formula anywhere you see a k value. So the first term will be 1 divided by 1 squared, and then we add when k is equal to 2 and plug that into the formula. So we have 1 over 2 squared, and then we add when k is equal to 3 and plug that into the formula so that we have 1 over 3 squared, and the next term would be 1 over 4 squared, and so on. The k values run from 1 all the way to infinity. And you might recall from the last video that this infinite sum is equal to pi squared divided by 6. So the formula by Ramanujan might look a lot more complicated, but the idea is essentially the same. And you would start with k equals 1, and anywhere you see a k in this formula, you would plug in k equals 1 for the first term, and then add when k equals 2, plug that in anywhere you see a k, and so on. And there are an infinite amount of these terms. And the remarkable thing about this formula is that it produces 8 digits of pi per term. So when you plug in k equals 1, that term will give you 8 digits, and then you add when k equals 2, and that will give you another 8 digits, and so on. And Bill Gasper used a variation of this formula to find 17 million digits. And after Gasper, in the year 1987, the Chudnovsky brothers discovered a similar formula for pi, which I'll write really quickly as 1 divided by pi is equal to this infinite sum. And as you can see, this formula is similar to Ramanujan's, although it is a slight bit more complicated. Though the idea of how to deal with this is the exact same. So with this infinite sum here, you start with k equals 1, and anywhere you see a k in this formula, you plug in k equals 1, and then you add when you plug in k equals 2 for the second term, and then you add when k equals 3 for the third term, and so on. And each of these terms is multiplied by this constant on the outside, 12 divided by the square root of this number here to the third power. And the remarkable thing about this formula is that it produces 14 digits per term. And the Chudnovsky brothers used this in the year 1989 to calculate 1 billion digits. And many people in the years to follow would use variations of this formula to continually increase the record of digits. For instance, in the year 2009, the record reached 2.7 trillion digits, and then in 2011, the record surpassed 10 trillion digits of pi. And this record was reached by the Japanese mathematician Shigeru Kondo, and he was aided by the American Alexander Yi. So at this point, you might be wondering, why should we bother to calculate so many digits of pi, especially considering that the number has an infinite amount of digits? And the truth is that for any scientific application, we really only need 40 digits at most. So we need only about 40 digits for any scientific application. And with this 40 digits, you can calculate the volume of the known universe to an accuracy of 1 atom. So in other words, the volume of the known universe. So you can imagine having a sphere where you enclose the entire known universe within the sphere. And remember that the formula for the volume of a sphere is 4/3 multiplied by pi times the radius of the sphere cubed. And by using this 40 digits, we can find an accuracy of 1 atom. And to give you an idea of exactly how small 1 atom is, a 150-pound person has about 7 times 10 to the 27th power atoms in their body. And this number is a 7 followed by 27 zeros. So it becomes clear that atoms are extremely tiny. So an accuracy of 1 atom is remarkably precise. Though it's also true that for much larger digits of pi, for instance these 10 trillion digits here, are useful for testing the accuracy of supercomputers. So in other words, we use these digits to make sure our supercomputers are functioning properly. And this is the end of the history of pi, though I have more videos covering many of these topics in much more depth.